I had this moment last night. I think a lot of you have probably had it. I was plugging in my phone, seeing that little green lightning bolt pop up, and I realized I have this total mental shortcut for how it works. I just treat the battery like a gas tank.
Oh, yeah, the bucket analogy.
Exactly, a bucket. You pour electricity in from the wall, you pour it out watching videos. Simple, right?
That is probably the most common, and I'd say the most dangerous oversimplification in modern tech. If your iPhone battery was just a bucket of electrons, your phone probably wouldn't turn on half the time.
Okay.
Or, given the energy density, it might just catch fire.
Well, that's a terrifying thought to kick us off. But this is exactly why we're digging into this today. We've got a pile of technical schematics for the iPhone 14 Pro Max here. Specifically, we're looking at a breakdown from a repair expert, Wintesla knock. And the big takeaway from these documents, and trust me, they are dense, is that the battery is not a bucket. It's a negotiator.
A negotiator, yeah. Or a command center. It has a brain, it has a pulse, and it's constantly having this high-stakes conversation with the rest of the phone. And if even a single word of that conversation is misunderstood, the whole system just goes dark.
So that's our mission for this deep dive. We're going to trace that conversation. We'll follow the electricity from the connector through this sandwich board architecture, which we'll get to all the way to a resistor that is literally smaller than a grain of sand.
And understanding that journey is so key. When Tesla Knock uses this phrase in the source material, it really framed it for me. He says, understanding the battery line is like buttoning the first button of a shirt.
I highlighted that too. Such a simple image. If you get that first one wrong,
the whole thing's crooked. It doesn't matter how perfectly you button the rest. In repair terms, you could have a perfect screen, a flawless CPU, brand new battery. But if you don't understand how power enters the system, that first button, your diagnosis is just wrong. The phone stays dead.
All right, so let's button that first button. Let's look at the map. The source material calls the iPhone 14 logic board a sandwich. Now, I usually think of a circuit board as, a flat green city, but this is vertical.
It is. It's a solution to a geometry problem, really.
Yeah.
We want all this stuff in our phones, 5G, multiple cameras, LiDAR, and we just ran out of floor space.
So you can't build out, you have to build up.
Exactly. Skyscrapers instead of suburbs.
Yeah.
You have a top board and a bottom board soldered together. It's incredibly dense.
And the notes mention this layer in the middle, the interposer. It sounds like something out of a sci-fi movie.
It does.
But it's just the filling of the sandwich?
Think of it more like a massive, complex bridge system.
Yeah.
Because here's the problem. The battery connector might be on the top board.
Right.
But the chips that actually need that power to wake up might be on the bottom board.
So the electricity has to commute. It can't just flow across
Exactly. It has to jump the gap.
a flat plane.
And it does that through the interposer. On the schematics, you see these little dots or pins like 321, 322. Those are the bridge pilings, the physical connections from one floor to the next.
And the source makes a really critical point here for repair. If you split the sandwich,
The bridge is out.
the traffic just stops.
Yeah, and it's a huge headache for technicians because you can't test the phone while it's apart. The lifeblood, the main battery power, it's cut off. The brain is separated from the heart.
It's amazing how fragile these solid bricks of metal really are. And speaking of navigation, let's talk about reading these maps, because looking at a raw circuit diagram, it looks like a subway map designed by someone who hates people.
It can be really intimidating, thousands of lines crossing. But when Tesla Knock has a great analogy for this, the street name concept.
This is what made it click for me. The idea that you're driving on a road, it's one continuous piece of asphalt. In your town, it's Main Street. Then you cross a bridge, and suddenly your GPS says you're on Highway 10.
Right. Same road, different name because your context changed. Electricity in these schematics works the exact same way.
So walk us through our main road here. What's Main Street for the battery?
Okay, so you start with VCC PBD. That's your Main Street. Raw, unfiltered power right from the battery connector.
The highway coming into the city.
Right, but then that electricity flows through a component, maybe a fuse or a resistor.
And after that, checkpoint.
New name. It might become analog PMUI BATT. Physically, it's the same stream of electrons, but that name change is a landmark. If you don't notice the street name change, you're lost.
There's one landmark here that really stood out, mostly because of its name. The chip that manages charging is called Rubicon.
Ah, yes. U4000. The Rubicon.
That's so dramatic, crossing the Rubicon. Why that name?
Apple engineers have a history with this. In older phones, the charging ICs were named Tigris and Yangtze.
Rivers.
All rivers. It's about flow. Current is basically fluid dynamics, so Rubicon is fitting because it's a huge decision point. It's the gatekeeper.
What's it deciding? I just plug in the cable.
It's the traffic cop. It sits between the battery, the charging cable, and the rest of the phone, what we call VDD main. It has to decide, okay, power is coming from the wall. I'll send this much to the battery, but I also need to let this much pass through so you can watch YouTube while you charge.
So if the Rubicon fails...
The river dries up, or it floods. Either way, it's bad. The phone might refuse to charge, or it won't let the battery power the system. It's a critical point of failure.
Okay, so we have the sandwich, the street names, the Rubicon River, but we started by saying the battery has a brain, that it's talking.
This is where we get into the gas gauge.
Right, GG is all over the schematics. As a gamer, I immediately thought, good game.
Not quite.
So GG is gas gauge, or fuel gauge.
Exactly.
Which brings us back to my car analogy, which you said was dangerous.
Because a car's gas gauge is dumb. It's a physical float in a tank. Liquid's high, floats high, needle says F. It's a rough estimate.
And the iPhone needs to be smarter.
Infinitely smarter. It needs to know battery health, cycle count, temperature, all of it. A float can't tell you that. So it uses a communication protocol called I2C.
I2C. I squared C.
Correct. Integrated circuit. It's a digital language. The source calls it a two-way street, which is perfect. You have two lines, SDA and SCL.
Okay, break those down. SDA is data.
Serial data. Those are the words. I am at 80%. My temperature is 35 degrees. I've been charged 400 times.
And SCL is clock.
Serial clock. This is the one that tricks people up. It's not the time of day. Think of the clock line like a drummer on a Roman galley ship.
Keeping the rhythm.
Exactly. It's a pulse. Tick-tock, tick-tock. It makes sure that when the battery speaks, the CPU is listening at the exact same speed. Without that rhythm, the data is just noise.
So the phone is constantly interviewing the battery.
Constantly. How are you? Are you hot? Can you handle a peak performance demand? And the battery answers over that I2C line.
I noticed in the analysis they pointed out a physical difference on the 14 Pro Max connector. More pins?
It does. It suggests a more complex negotiation. Bigger battery, higher power demand, probably needs extra sensing or ground pins to stabilize that interview. But the basic principle is the same. Digital chatter.
Okay, that's the digital side, the talking. But then the source pivots to what they call the first button, the critical part, the sense lines. And this is where the distinction between the phone asking how the battery feels and the phone checking for itself became really clear.
This is the aha moment. This is where so many repairs go wrong.
Because I can ask you, hey, how much money is in your pocket?
Yeah.
And you can say, $100, that's the I2C.
Right. And I could be lying or just mistaken.
Exactly. The sense lines are me physically taking your wallet and counting the bills myself.
That's a perfect way to put it. Trust but verify. The I2C is the report. The sense lines are the reality check.
And to do this, the phone uses two microscopic resistors, R3701 and R3T702.
These are the guardians. R3701 is a 1 kilo ohm resistor. R3702 is a 9.53 kilo ohm resistor.
Okay, I have to stop you. 9.53, not 9.5, not 10. That is incredibly specific.
That precision is everything. The source notes, they have a 1% tolerance. They have to be almost perfect. R3701 measures current, the flow. R3702 measures voltage, the pressure.
The source used an analogy I loved here, splitting a hair.
Because the margins are just that thin. Basically, electricity flows through this tiny resistor. Because there's resistance, it creates a tiny voltage drop. The power management unit, the PMU, it measures the pressure before the resistor and after the resistor.
And it compares the two numbers.
And the difference between those two numbers tells the phone exactly how much power is moving. It's Ohm's law on a microscopic scale.
Now here's the scary part. These things are smaller than a grain of sand. If you drop your phone or a bit of water gets in, what happens to R3701?
It can get what we call stretched.
Stretched like a rubber band.
Not physically, but its electrical properties change. Its resistance value drifts. That 1K ohm resistor might drift to 1.2K ohms.
To us, that's nothing.
But to the PMU, it's a catastrophe.
Yeah.
Because the math stops working. The PMU does the math, assuming the resistor is a 1K ohm, but it's actually 1.2K. The result is garbage. The phone thinks, whoa, there's way too much current, or I can't even detect the battery.
So even if your battery is brand new, 100% healthy,
The phone panics. It'll refuse to turn on. Or it will boot loop. You see the Apple logo, it fails the safety check, shuts down, and tries again. Forever.
that is wild. A $1,200 device is a paperweight because a resistor the size of a dust might drifted by 0.2 ohms.
EME technicians will miss this. They'll change the battery, still dead, change the port, still dead. They'll say the motherboard is fried. but they just needed to measure R3701.
It really is the first button. If that resistor is wrong, the entire diagnosis is wrong.
Precisely. And this gets to an important distinction. Analog versus digital signals.
Right. So the gas gauge, the I2C talk, that's digital. Zeros and ones.
Yes, the digital is language. It's clean symbols. But the sense lines,
Yeah.
those are analog.
Analog is the real world.
Analog is continuous. It's messy. It's the actual wave of electricity. The sense lines feed that raw, real-world signal into the PMU, specifically to pins J10 and E12.
And the PMU is the translator.
Yes, the PMU, the U3300 chip, is the heart. It takes that analog blood pressure reading, converts it into a clean digital report, and sends it to the brain, the CPU.
So if the analog reading is wrong from a bad resistor, the report to the brain is fake news, and the brain shuts the whole body down.
You've got it. It's a fragile ecosystem. Every year, it seems to get more sensitive.
They just keep making the nervous system more complex.
They have to. Think about fast charging. You're pushing 20, 30 watts into this tiny lithium pouch. You need to know exactly what's happening in real time. You can't just rely on a slow digital report. You need those sense lines to be accurate to the millivolt.
That 1% tolerance makes a lot more sense now.
It's all about safety, preventing overheating, overcharging.
So let's just recap the full journey we took. We started at the battery connector.
Which is more like a docking station than a plug.
Right. Power travels up through the interposer, the bridge in the motherboard sandwich.
If the bridge is down, the city goes dark.
It crosses the Rubicon, the traffic cop managing flow from the wall.
And keeping everything stable.
And finally, it passes through those sense resistors, R3701 and R3702, the tiny gatekeepers that measure reality.
The tiny components that decide if your phone lives or dies.
It really changes how you look at the phone. It's not a solid block of magic. It's this incredibly delicate balance.
It is. We obsess over megapixels and terabytes. But the heartbeat of the machine is in these microscopic analog lines. Wintesla Knox analysis shows you can't just be a parts swapper anymore. You have to be a cardiologist for electronics.
A cardiologist for electronics, that's a fantastic way to put it.
It's the truth. You're navigating a map where street names change and the critical sensors are smaller than dust.
And that brings us to the end of our trace, from the connector to the core. A good reminder that sometimes the most important part of a system is the one you can barely see.
Absolutely. The 1 kilo ohm resistor. The unsung hero.
So, here's a thought to leave you with. We trust these devices with our lives, assuming they're these robust, solid things. But deep inside, there is a component smaller than a speck of dust whose only job is to feel the electricity. If that tiny speck gets confused or drifts just a fraction, the whole system vanishes instantly.
It raises a kind of philosophical question for our time, doesn't it? If the phone can't feel the battery, does the battery even exist?
Deep thoughts for a deep dive. Thanks for listening, everyone.
Stay curious.
Hey there, and welcome. So, you ever look at that little battery icon on your phone and just take it for granted? You just trust it, right? Well, today, we're going to pull back the curtain on what that number really means. Because behind that simple percentage is a secret story, an insanely fast conversation happening deep inside your phone. So, that's the big question we're tackling. How does your phone actually know its battery percentage? You'd think it's simple, kind of like a fuel gauge in a car. But the truth is, it's way more complicated and honestly, way cooler. It's not a simple measurement. It's a constant, complex calculation. You see, the secret is that your battery and your phone's brain are always talking. It's this nonstop, high-speed dialogue, all written in the language of electricity, that turns the raw chemical power in the battery into that tidy little number you see on your screen. Okay, so to follow this conversation, we're going to need a map. And this schematic right here of an iPhone 14 logic board, this is going to be our guide. We're going to trace the path of both power and data, kicking things off right where the battery plugs into the board, at a spot called J10400. So, our adventure begins on this main power line, which you can see highlighted in red. The technical name for it is PP_VCC_BATT. The easiest way to think about it is like a massive electrical superhighway, just pumping raw power from the battery out to the rest of the phone. Now, here's where it gets really interesting. This circuit board isn't just one flat thing. It's actually more like a multi-layered sandwich. You've got a top layer and a bottom layer, and all the really complicated stuff, all the circuitry, is packed in between them like the fillings. And for that power and data to get from one side of our sandwich to the other, it has to travel through these special little connection points called interposers. It's kind of like an elevator between floors. This is how all the different layers talk to each other and make this whole electrical ballet happen. All right, so our power has left the battery, it's zipped between the layers of the board, and now it's arriving at its first major destination. That electrical highway flows right into this super important chip, U4000. Its nickname is Rubicon, which is pretty cool. There's a tradition of naming these big power management chips after famous rivers. So the Rubicon chip acts like a gatekeeper. It handles the whole charging process, and it's one of the very first things to read data coming straight from the battery. But here's the kicker. That big red power highway, that's just raw energy. The real magic, the actual secret language of the battery, is happening on these much smaller, more delicate pathways, the data lines. This is where the actual information, the conversation is happening. Now, these data lines have some seriously intimidating names. I mean, they look like something straight out of a sci-fi movie. But if we actually stop and break them down piece by piece, we can decode them and figure out exactly what they're saying. The language they're all speaking is a protocol called I2C or I2C. Just think of it like the grammar and the rules of the road for any conversation happening on the circuit board. It's a super efficient little two-wire system made just for chips to talk to each other up close. So let's decode one of these monster names, I2C2 underscore SMC underscore charger underscore BI underscore GG underscore SDA underscore 1.8. I know, it looks like a mess, but it's actually a sentence. I2C2 is the language. SMC is who it's talking to, the system management controller. Charger, well, that one's easy, it's about charging. BI tells us it's bidirectional, a two-way street. GG is the really key part. It stands for gas gauge, which is literally the thing measuring the battery's capacity. Then, SDA just means it's the serial data line, and 1V8 tells us it does all this using just 1.8 volts. See, it's not so scary once you break it down. So all this data, the power levels, the gas gauge info, all of it is flowing from the battery through that Rubicon chip, and it's all headed toward one central location, the command center for the entire power operation. Okay, so this is super important. We've got two main characters here. The Rubicon chip is kind of like a field agent. It's on the front lines, handling the charging and gathering the raw intelligence from the battery. But the power management unit, the PMU, that's the boss. It's the heart of the whole operation. It takes in all the reports and makes the final calls on where every single drop of power goes. And you can see it right here on our map. All the roads we've been following, both for power and for data, they all lead to this one chip, the U3300 PMU. This is the final destination for all that critical information. And man, the PMU is a serious multitasker. It's constantly reading that gas gauge data from Rubicon, it's checking the real-time voltage and current draw, it's protecting everything else from power surges, and here's the big one for our question. It takes all of that information and does the final calculation. So after this whole journey, all this traveling through the board, all the decoding, all the calculating, we finally get our answer. And it shows you just how vital this whole system is to everything your phone does. And there it is, mystery solved. It is the power management unit that does the final math. It takes all that raw data, it looks at the voltage, the current, the temperature, even how old the battery is, and then it sends one single finalized number to the phone's main brain, the CPU, which is what you see on your screen. You know, when you zoom out and look at the whole schematic, it looks like a bustling city at night. It's this huge network of components, all powered and perfectly controlled by this incredibly sophisticated system of checks and balances, conversations and commands. This power network is literally the foundation for everything else your phone does. And all of that, this entire ridiculously complex dance of electricity and data that's happening thousands of times every second. It's all going on just to give you that one simple, trustworthy number. It's an incredible amount of complexity hiding in plain sight. It really makes you wonder, doesn't it? What other secret worlds, what other complex conversations are happening just beneath the glass surfaces of the technology we use every single day? Pretty amazing to think about. Thanks for digging into this with me.